It's my great honor to introduce our speaker today. Dr. Jing Li is an associate project scientist at UCLA in Department of Earth, Planetary, and Space Sciences. She got her PhD from University of Paris 7, and after that she worked at Harvard Smithsonian Center for Astrophysics, University of Hawaii, and UCLA. Jing has been working on solar magnetic field in both observation and theory since 1985. She is currently focused on the interpretation of the solar dynamo from observations. She also studies the asteroid and comet using solar spacecraft data. And she is also interested in the relationship between the solar wind and geosynchronous energetic particles. We apologize that due to a glitch in the recording, we missed the title slide of Jing's seminar in the very beginning, and we are now starting from her introduction part. Thank you.
Continue this work, I use I use the spacecraft data this time, not the ground-based telescope, not ground-based data. So we'll try to do a thematic study of the Hill and anti-Hill sunspot physical parameters. So basically the data consists of from MDI and HMI for cycle 23 and 24. So my presentation is basically one Yang told me, asked me to give a talk. So because it's been done quite a while ago, so I kind of forgot the details. So I started to put the data from two papers together and try to see if I can reproduce the results that from these two papers. So now this presentation will be the data that I gathered from this previous work and in a new kind of display, but results will be same as with two papers. So so this is the plan of the talk. So in this talk, I think my talk's not very long. But there's some big tables, and I will try to explain more carefully. And in the beginning, I will talk about the motivation of the study, and we'll briefly describe the data. I basically just describe a little bit. And the analysis technique will be brief. And the presentation of the results of this basically 4 cycles of analysis of the data, sunspot data. And in the end, I will give a summary. So motivational talk is really the sunspots is a manifesto of the solar inner work, solar dynamo's inner work. So this is a Babcock-Little model, basically started with the sun as a dipole. As the sun rotate around this, it's rotating, then the magnetic field dipole is stretched along the gradually parallel to the longitude direction to the equator. It's because in the equator the rotation is faster, and in the near polar region rotation is smaller. So it has a this different rotation. Then as the cycle progressed, the sunspot started to appear at first in the high latitude, then gradually going down to the low latitude, I guess, along this magnetic field line, this dipole field line. And because of a meridian flow, so the sunspot has the following part is pushed to the polar region, and the leading part gradually emerge from the lower latitude in the equator. Eventually, they cancel each other at the equator, and in the polar region, and also the magnetic field cancel each other because the solar following part of polarity is the opposite from the polar region. So when the new cycle started, the polar region polarities changed the sign. So if this positive in the north, it will be negative polarity next cycle. The south is the same. So that's the Babcock model. And So the next one is that how the sunspot emerge from the deep inside the sun. So that is the work of the hydromagnetic dynamic physics. So basically, when you have a magnetic bubble generated in the bottom convection zone, as most people seem to think about that. So the magnetic bubble became inside its density is lower than surroundings, so it becomes buoyant from the convection zone, rapidly ascending to the goes through the convection zone and eventually to the surface. As this magnetic bubble, called the magnetic field tube, emerge as rapidly ascending, and it feels the force that's called a Coriolis force because of the solar rotation. The Coriolis force acceleration, as I listed here. Sorry. Okay. So the Coriolis force acceleration is listed is shown in the on the slide, and for the local magnetic flux, it feels the solar rotation is omega phi. Phi is the latitude, with a sign phi. So this is in the local plus you will feel this kind of rotation. Then in the effect, the Coriolis force will twist this flux from originally along the longitude direction, twisted towards to the equator. So the leading polarity is has a lower latitude than following polarity. So it's kind of tilted. So if we can measure this kind of magnetic tilt, the angle, and so that'd be great. Will tell us something. So because of this Coriolis force, this kind of tilt angle will be related with sunspot latitude in the relation in the bottom of this slide I show. So I would like to reminder about Hill's law. Because of the Babcock-Linden model, it quite explain well the Hill's law. The Hill's law is that they look, for example, they look at this magnetogram that I just downloaded yesterday off the internet. So if you look at the northern hemisphere, you saw a majority sunspot has a white patch in the right and a black patch in the left. So the in the right is called the leading part, then in the right called the following part of the sunspot polarity. White represent the positive polarity, magnetic polarity. Black part represent the negative polarity. So in the northern hemisphere, mostly positive polarity is the leading part of the sunspot, and the negative in the following part. And in the southern hemisphere, if you look at south, the black is in the right, and the white is in the left. So this kind of polarity arrangement switch the sides, to the opposite in both between the hemispheres. And this is part of Hill's law. And another part is that this is right now we are in the cycle 24. So when the cycle 25 comes, or previous cycle, this kind of polarity sun switch the position. So in the north, in the cycle 25, most sunspot will have negative polarity in the leading as a leading component, and the positive as a following component in the north, and the south is the opposite. So that's the Hill's law. And Joyce's law is that if you look at the sunspot, for example, a big one in the center in the north hemisphere, that is the polarity line, the polarity pair lines kind of tilted towards the equator. And next to it in the right side, another big sunspot, the tilt angle at the lower latitude, the tilt angle is kind of a little flat. So the Joyce law basically say this tilt angle towards the equator, will increase with increasing latitude. So when near the equator, the tilt angle will be small, and away from equator at the high latitude, tilt angle will be big. So that's Joyce law. As function, actually, Joyce law I think is kind of reflect the Coriolis force act on the sunspot flags. So the next part is the data and what the data type we use. So there are two types of data. One is the sunspot record. So the sunspot record mostly on the left is from Mount Wilson. They have their own sunspot record. And on the right is a more modern sunspot record that we use daily, published daily. So for the basically what I use is mostly the sunspot location and the time. So that's marked with red color. So those information I will use in the analysis. And the next one is longitude magnetogram. So this is there's three the magnetogram from three different instruments as shown here. And you can see that the three magnetogram, the magnetogram from three different instruments have quite a different pixel resolution. But for our analysis, this is not very crucial because we basically just grab catch the majority of catch the sunspot magnetic area, then measure the different measure various physical polarities. So this is the magnetogram I'm using. So basically, I use a sunspot record located for the initially located the sunspot on the magnetogram, match the time and the location. Then I do the calculation. So this is an analysis technique. How do I do it? So the first we locate the sunspot center position on the magnetogram using those sunspot location and the time. And then we determine the dipole area. And once we capture the majority of the sunspot area, we got the size and the center position and the polarity pair, the size of the polarity pair that is marked with yellow and red color on the left panel, the 4 different sunspots, and the oval shape, with white oval shape. That is the area that we include. Basically, our calculations inside this area as counted as a sunspot magnetic area. So once we found the sunspots, we collected the information, the pixel size, the information, the magnetic field, magnetic flux, and the position, all these things, and we can calculate the tilt angle. But maybe, and then we can redefine the oval size, because once we have the positive and negative size, that is we can and the distance between these two polarities, that we can redefine the size of the oval shape. That is A is the semi-major axis of the oval shape. Then semi-minor axis we just define as a half of A. So we repeat this in the computer, repeat this step 2 to 4 until we calculate the tilt angle became stable in this process. So that's the example. Oh, sorry. Is that my internet?
I can hear you.
Yeah, we can hear you okay.
No, but I'm trying to change the slides.
Oh.
But I cannot change it. I don't know why.
Can you try maybe stop sharing and share again?
Okay.
Is the iteration over time? I'm not sure what the
Okay,
iteration
now it's moving. It's examples page.
What's the question?
You say you iterate, but I'm not sure what over. Like, are you iterating in time, or are you changing the oval size? And what's the iteration over? I'm not sure.
This graph basically explains how iteration worked. So the white oval shapes is when the iteration is doing the work. Then the black is the resolution. So you can see that the tilde angle is changing. In the beginning, tilde angle is kind of flat. I basically always say the tilde angle is 0, but gradually the computer will change the tilde angle to the mostly aligned with the sunspots magnetic tilde angle. So in the end, the black circle, black oval shape, is kind of fit to the magnetic pair tilde. So on the right is shows the final result. Oh shoot! Why can't I not change the slide?
Currently, we're seeing the examples slide. Do you want to try stop sharing and share again? Just now, when we were talking about it, it seems to move forward one slide, but it was maybe
yes. This slide is I'm going to talk about.
Why don't you quit Keynote and start it again? Could try that.
Okay, leave. Wait.
Oh, it's now measure the parameters.
Your screen sharing. So stop sharing.
No, quit Keynote.
Keynote. Oh, can I quit that? Okay. Oh, okay. So, okay, I want to show this slide now. Let me see if it works. Yeah, so this is following the previous one. Then this shows the parameter that I can measure from this kind of measurements. So one is the sunspot numbers, of course. So each sunspot I can, so each sunspot has, you just count the number. And the sunspot center of the mass position, I can get X and Y, all longitude and latitude. And the magnetic flux and the magnetic area, they are basically equivalent. Magnetic flux I can get the two polarity separately, negative and positive, and the total magnetic flux just sum of the add them together. Polarity separation is the separation between positive and negative center, the distance between these two centers, measured in the kilometer. And the last one is the polarity pair tilde angle, gamma. So that's the angle that in the iteration we've been trying to match. Oh, I don't know why. Oh. How do I the Keynote? I try to quit Keynote.
Okay. Oh, it's now new page.
Yeah, it's not a new page. But why this?
Now
Keynote?
it's Sunspot studies. I think that's the
yes,
next
right.
one.
Oh, sure.
I feel it's just the time
Oh
delay.
yeah, so now seems normal now. I don't know why.
Okay.
Oh. No. I try, okay. I want to go through. Okay. So this one I want to show. Okay, this is sunspots started. This is number of sunspots in the north and the south. And the data source in this presentation, I use Mount Wilson observatories for cycle 21, 22, and FDI for 23, and MDI plus MHI for 24. And because we can get from analysis, we can get the sunspot position, so we can draw this butterfly diagram. And the red arrow shows mark the beginning of each cycle. So this is 4 solar cycles we are going. I'm going to include in this presentation. So for cycle 24, the data only the data ends in 2018, but 24 is I think ending in 2019. So it's 1 year short, but should still be okay for the statistics analysis. Before I go any further, I would like to explain this tilt angle definition. So for the calculation of the tilt angle is shown in the bottom in this equation. So tangent tilt equals the latitude difference divided by latitude longitude and the cosine latitude average between 2 polarity average. So the tilt angles, the angle, if they change between minus 90 to 90 degrees, that means positive polarity is the leading component, negative is a following component. But if the tilt angle the number is from 90 to minus 90, so 90 to 180 to minus 180 to minus 90, that means the leading polarity is negative. Okay, so this kind of definition is convenient to show Hill's law. So this diagram shows that each dot represents a sunspot, and the sunspot tilt angle as function of time. So look at the cycle 21. There's a cluster of the right spot near the tilt angle equals 0. That means that based on our definition, the leading polarity is positive, and the red one is sunspot from northern hemisphere. Blue dots as the sunspot from southern hemisphere. So in the north, in the cycle 21, the leading polarity is positive, and in the south, the leading polarity is negative. That's the blue one represented near the 180 degree. So this kind of pattern switch from cycle to cycle. So it's very good to show that how the Hill's law played out with a sunspot. And you can also notice that there are some, there are some red in the just say cycle 21. There's some red spot, but near the 180 degree, 120 degree. Those spots are actually they don't follow the Hill's polarity rule. So they have polarity, leading polarity because it's negative, opposite. Although they are in the north, but the opposite from the normal Hill's law polarity. And also you can see that the cluster near the, just say near the tilt angle 0 is a little bit off from 0. Yeah, they normally the tilt angle not exactly 0, but they still, in average, they are still has a little bit tilt from the equator. That is kind of a majority of the sunspots. So that actually tells you kind of the Joyce law. But in this graph, it's not so clear. And okay, so this graph shows the sunspot, sunspot in the from cycle to cycle, from hemisphere to hemisphere, and two groups of sunspot. One is a hill sunspot and one is an anti-hill sunspot. There's the number of the sunspots and the percentage of the sunspots at that hemisphere, at that cycle and hemisphere. So basically, the hill sunspot is about 90 degrees of the total sunspots, and the anti-hill sunspot is about 10 degrees or less. This things doesn't vary from cycle to cycle and from hemisphere to hemisphere.
Jing, can I ask a question about when you record the tilt angle? You may have already said it, but I didn't capture it. Do you record the tilt angle when it is at its maximum flux or when it's at the central meridian?
No, I recorded tilt angle this program iterate until the tilt angle becomes stable, basically. Because I assume I already include all the magnetic flux in the sunspot in the beginning.
So you're recording the tilt angle over time, and then at a certain point it becomes stable for a certain amount of time before it changes again?
What are you talking about? Are you asking me how to determine the tilt angle, right?
No, well, I'm asking, do you have in your data set, say, you know, the 10% that are anti-hail, does each sunspot group only have one tilt angle?
Yes.
And that tilt angle is determined at only one time. And I'm asking, and you're saying it's determined at the time when the tilt angle is the most stable, but I don't understand.
For the Mount Wilson data, as I remember, is they have the daily average magnetogram. So each sunspot has 1 magnetogram each day.
So in the Mount Wilson data, you would have one sunspot group would have multiple tilts contributing to the data set.
Right. Yes. Yeah.
And in HMI and MDI, are there multiple tilts at what?
Yes, I think I choose near the center the tilt angle.
The central meridian?
Central meridian, yeah, when they close to the central meridian.
Okay, so it's only determined once a day, but you showed the tilt angles being determined all over the disk. You know, when you showed that image, there were sunspot regions at, 30 degrees off central meridian that had tilt angles. So I'm just wondering how many times a single sunspot group contributes to the database, and if it's only once, when that's determined.
Yeah, actually these sunspots, I think in this data set, I just have one sunspot, just single sunspot. One sunspot just there's no multiple
entries.
Yeah, just one sunspot.
And you think it's at central meridian?
I think the central meridian or maximum flux. I'm not sure. I need to think about it.
All right, thank you.
I think that doesn't make much difference statistically. Should be okay. And I also think the anti-hill sunspots are real. They are not, but they are not as numerous as maybe a few percent, I think, less than 10%. So this is another plot to show the sunspot tilt angle distribution. So in this polar coordinate, the radial direction is latitude. In the center is if you look at the northern hemisphere, the center is 0 degree and goes up the latitude increase. The surrounding circumference represent the tilt angle measurements. So tilt angle change from 0 degree to 90 to 180, then to minus 90 back to the 0 counterclockwise. So each spot represents the sunspots, and the orange one represents the Hill sunspots, the yellow one represents anti-Hill sunspots. So in this particular cycle 22 give you an example that the sunspot tilt angle in the north is between 90 to minus 90 degrees. So that means the negative polarity is in the leading component. But the anti-Hill sunspot is the opposite. And to the south is the opposite. So the leading component, so the sunspot tilt angle is mostly vary between minus 90 to 90 degrees. And that means that they have a leading polarization positive, opposite from, so majority sunspot. And there's some sunspot also on the left, light blue, they represent anti-Hill sunspots. And also you will notice that on the northern hemisphere on the left, there's more sunspot concentrate between like 120 to 180 degree in the tilt angle. So that actually represent the Joyce law. That's the tilt angle that towards to the equator, they change. But when the tilt angle changes from minus 180 to minus 90, that's still Hill's sunspot, but the tilt angle is tilted away from the equator. So same as the southern hemisphere, the more the sunspot, many sunspots concentrate on the on the section from 0 to 60 degrees in the tilt angle. And also there's some considerable number of sunspots distribute from like a minus 60 to 0 degree. Those sunspots also has the tilt angle tilted away from the equator in the southern hemisphere. And the Joyce sunspots is tilted towards the equator in the southern hemisphere. So this kind of graph shows you the pretty clear that Hill's sunspot and anti-Hill's sunspots where they stand. And you saw from cycle to cycle, they oscillate from cycle to cycle. So the top row represent the northern hemisphere, then the bottom row represent the southern hemisphere, and each vertical is represent a cycle, a different cycle of the how the sunspot tilt angle change. In order to describe to investigate Joyce law, I feel that it needs to introduce the tilt angle in the right box defined. So this kind of tilt angle change from minus 90 degree to 90 degree. Instead of the fundamental tilt angles change from minus 180 degree to 180 degree. How I do it is that I just take the fundamental tilt angle, the definition from the right side of the box, and just if they happen to be between minus 90 to 90 degree, I just keep them. You know, that's okay. But if they happen to be between 90 degree to minus 90 degree, so I basically just from 90 to 180 degree, I just change into the tilt angle from minus 90 to 0 degree. So it's like if you have a line, so you don't change the tilt angle, but you change the kind of number and change it, make it change between minus 90 to 90 degree. So with this kind of definition, So you don't care about polarity, which one is leading, which one is following. You just care about the orientation, how they tilt. So when the tilt is positive, that means that the sunspot is tilted towards the equator. That's correct tilt. If it's negative, the tilt will tilt away from the equator. So that's plot. So in the north and the south is, also has a definition different. The purpose is to analyze, to investigate the tilt angle as function of latitude that fit into the equation in the bottom, in the gamma equals k phi. Phi is latitude plus b phi. So try to fit this in this equation to get the parameters. So this graph I took from the paper. This graph basically shows two things. One is that it's a part of the butterfly diagram, it's in cycle 23, basically. During this period, both Mount Wilson and MDI have the data, so we can compare them for the same sunspots. So so basically on the sunspot for butterfly diagram, the sunspot latitude vary as function of time. That is represented by those plus symbols in the background. Those are the sunspots, and those lines, red lines represent the tilt angle measured from Mount Wilson data, and the blue lines represent the tilt angle measured from MDI data. So basically, the tilt angle measured from two instruments don't differ very much. So we can kind of trust this kind of measurement. This gives an example how I try to fit to get this linear fit with all the sunspot data. So basically, we use all the sunspot from one hemisphere or separate fit for the hill group and anti-hill group. So on the left side, you can see that the sunspot tilt angle is function of latitude. The orange one are the hill sunspot. The yellow one are the anti-hill sunspot. They are fitted separately to this equation. On the right side is the southern hemisphere. Blue one are the hill sunspot. Yellow one are the anti-hill sunspot, and they are fitted differently too. So now it's this big table show the fitting results. So this shows from the cycle by cycle, from each cycle and the hemisphere separately, different hemisphere, and the K phi, the column in the hill sunspot, anti-hill sunspot, in the columns, one is K phi, the parameter fitted, and the B phi, and the average tilt angle, the third column, and the fourth one is the medium tilt angle. So this kind of average medium cannot tell you how the tilt angle is scattered in the sunspot group. So you will see there are two things I like you to notice that one is for the hill sunspot, the correlation coefficient K phi is pretty good. Is higher than 3 sigma, except for the cycle 24 in the northern hemisphere and cycle 22 in the northern hemisphere. And for the anti-hill sunspot, the K phi coefficient, correlation coefficient is not so significant. So they basically, so that means that tilt angle and the latitude not quite related with each other. But for hill sunspot, it's very good. Another thing, second point I would like you to notice that in the hill sunspot, for K phi, there's a kind of hemispheric asymmetric for the K5, like cycle 22, in the north is much smaller in the south. For the cycle 23, south is smaller than the north, and for that it's opposite. So that's kind of interesting result, and maybe needs to be further investigated. So this is also I got from the paper, is the magnetic flux. Is the magnetic flux, actually it's the magnetic flux, compare the magnetic flux between Hill sunspot group and anti-Hill sunspot group. So Hill sunspot is plotted is a flux as function of latitude in the separate cycle 23, 24. And the Hill sunspot represented by blue curves and anti-Hill represented by green curves. So you can see that Hill sunspot in general, the flux is much higher, about 10 times higher than anti-Hill magnetic flux. How about the pole separation? So it's like the sunspot has a polarity pair, positive and negative. The distance between them should have some correlation with the magnetic flux in the system. So the whole system as a whole, if you were thinking that if the magnetic field is stronger, the pole may be more separated because they have this expansion just stronger. So indeed, this is an example. Another again for cycle 2022. Again, it's on the left side. The orange represented the left side is the north hemisphere. The measurement from northern hemisphere. The orange represent the Hill sunspot. The yellow represent the anti-Hill sunspot. The fit to these numbers. So the fit is I'm fitting the equations in the logarithm. So logarithm S equals K5 logarithm phi plus B5 using the linear regression fit. So the fit eventually, you can see the straight lines, orange and blue and green. On the right side, again, is blue is the Hill sunspot in the southern hemisphere. Blue is the Hill sunspot, and light blue is the anti-Hill sunspot, and also fit to each other, these two groups with a straight line. So this is another table to show the parameters of the fit. K5 is the correlation coefficient between logarithm S and logarithm phi in the Hill sunspot and the anti-Hill sunspot from different hemisphere and from cycle to cycle. So for the Hill sunspot, the correlation is very good, significant, pretty much. But for the anti-Hill sunspot, mostly except for the cycle 24 seem to be correlated, but the other three cycles don't have any correlation between pole separation and flux. That is the result. So again, remind you that this talk is based on these two papers. Thank you for Roger suggest me this measurement of the sunspot tilt angle. Also, I studied this. So this gave me the subject to further explore. That's very interesting. So here's the summary. Yeah, my talk is not that long. Okay, so the summary is the Hills and the Joyce laws are very clear in all data. That's pretty good. And the Joyce law is mostly the Joyce law is actually more significant for the Hills sunspot. Anti-Hill sunspot is not so much. Yeah. And the hill sunspot and anti-hill ratio is about 90 to 100 to 10. Yeah. So or maybe less than 10, greater than 90, something like that. So hill's magnetic flux is higher, about 10 times higher than anti-hill magnetic flux. And for the pole separation and the magnetic flux, for hill sunspot, they are quite highly correlated. Not for anti-hill, not so much. There's this sunspot number I think maybe I didn't emphasize in the presentation, that there's more sunspot number appear in the south than in the north by about 10%, except for the cycle 24. And there's also tilt angle asymmetry, as I just mentioned in that table, between north and the south hemisphere. Yeah, for the cycle, I think 22 and 24. Yeah. No, 22 through 24. Yeah. Okay. That's it. Thank you very much.
Okay, thanks to Jing. Question time.
There's a chat.
No, there. I asked people to ask during the talk directly. No question in the chat yet. Okay, we have a few hands raised for question now. So Robert first, and then Amy. Robert.
Yes. So I have a question about the anti-hail spots. So this is not just a tail of the hail spots, hail active regions. It's when you look at the plots, there's a clear gap.
This one?
Yeah, this one, for example.
Okay, this one.
Yeah.
So what is your question? You think?
So there's really a clear difference between it's not just one distribution with large wings. You're arguing that the population is very different.
Yes, the population, the hill and the anti-hill sunspots are very different in the tilt angle and the magnetic flux. And in the tilt angle, they don't obey they violate Hill's law and Joyce's law. So in average, anti-hill sunspots, the average tilt angle is tilt away from equator. The most well-behaved sunspot should be the tilt angle is tilt toward the equator, and their tilt angle change with latitude. That's the sunspot. Those sunspots are distributed between, on the left side, distributed between 90 to 180 degrees.
Okay. And what percentage of these spots near the equator, which are just the wrong polarity spots, or the polarity from one hemisphere, which just went into the other hemisphere? So I imagine if you're at 5 degrees or 2 degrees, you must occasionally pop up in the other hemisphere. Are these near the equator, or these are?
This is you mean on this graph, the latitude of the sunspot is in the radial direction. So when the sunspot is close to the center, their latitude on the left side, their latitude is smaller. So it's close to the equator. And on the southern hemisphere, actually, it's the same, right?
Okay, thank you.
So sunspot in the low mid latitude distribute, but for anti-hill sunspot seems all over the place.
Okay, I have a couple of questions. I don't know, where do you think, well, the first is the most general. What do you think Joy's law is being caused by? I
think it's correlated with the Coriolis force, because the Coriolis.
What velocity then is it acting on? What velocity is the Coriolis force acting on? The divergent flow, the flow in the flux tube, or what?
It's on this diagram. It's the pole separation and the solar spin, solar rotation.
So it's the divergent flow near the top of the atmosphere, or near the photosphere. Okay.
So like
At another point, I'd be interested to know how you calculated the error on your slopes, because we have a person in our group who's a student who's working on looking at Joy's law, and her calculations for the errors on her slope are about 3 times as high as yours. So just maybe not right now, but maybe I'll send you an email afterwards to see if we're doing something wrong with that.
High, really?
Yeah, I think it's about 0.3 or something, or 0.2, and yours are about 0.1.
Yeah, I didn't even do anything. I just simply did a linear regression fit to sunspot with this, different hemisphere and different hills.
And you're fitting all data points. You're not fitting to bin's data, right?
All the data points I have.
And the other question is this data available? Is the data set available for
I sent to you. I sent all these data, the data I already sent to you.
You sent it to a student, a PhD student of mine, Bruce McClintock, although he left and I don't know. I don't think I have the data, but I mean, I'm just asking if it's public, or if we could access it to compare to what we're doing.
Yeah, I can send, no problem. Yeah.
Okay, thank you.
Right. So I think my guess is that anti-Hill sunspot, because their flux are much smaller than the Hill sunspot, they probably the Coriolis force. So they are more influenced. They probably interact with the surrounding material when they ascend from the convection zone. So maybe that's why they are bumped, by the surroundings. So that's why they kind of lost the direction for anti-Hill. So that's kind of reflect how the convection zone, all this, how they worked, the flow. But in general, it's pretty. Yeah, I think in general the Hill sunspot may be interesting that for studying the convection zone, the dynamics. I'm not sure. I'm not the expert on that. But for Hill sunspots, I think because they have less interaction with the surrounding material in the convection zone, so they just pop out very quickly and ascend to the surface. That's why they can, Coriolis force act them strongly, because they expand faster. That's my guess.
I think that's all the questions. Any last chance? Any more questions? Okay, if not, we are actually right at the 1 hour time limit. So thanks again to our speaker, Jing Li, today. And thank you all for your attending the seminar and discussions. So once again, next month, we will have the October community workshop, actually October and November 3rd. So the community workshop. So hope to see you all sometime during the workshop next month, and also at next month's seminar. Okay, that's all for today, and see you next time.
Hey, thank you for coming.
Thank
Bye.
you, Jing.